Okay, and this is an improved version of CutRod using dynamic programming approach with memoization. The difference in this code is you have additional argument R. That R is created in the calling function in the main, and then that is depending on R. So initially this one is filled with negative infinite because this one is holding the result of CutRod. For example, here we have same P, prices tax, and CutRod P, and then given n equal 4 and all. That R is having only 4 spaces because n equal 4, and all places filled with negative infinite. So when you normally looking for maximum, you start from negative minimum infinite. You're looking for minimum, then I start from positive infinite. So they all filled with negative infinite for now. That means here I don't have any positive maximum revenue for a rod of 1 inch, but we are going to update as we find out. So here is a illustration, same prices starting with n equal 4. So let's see, this one has again the option 1 inch cut out as a first cut plus CL3, and then second option 2 inch out plus CL2, third option 3 inch out plus CL1, 4 inch out plus CL0, and then this program shows, hey, if it is 0, you don't quite need to check whether you have saved value or not. If it is not equal to 0, you're checking whether corresponding position of our value, L of n, is 0 or above. Then just use it because L of n is solution. L of n is the value of CutRod n. But if it is negative, you have to go through regular operation and then save it at the end. So here you go. So they don't have CL number 4. CL4, L1, 2, 3, 4, they're all negative for now. CL4, you don't have the value, go down. CL3, you don't have the value, go down. 1 inch out option plus CL2, 2 inch out plus CL1, and then 3 inch out plus CL0. Again, CL2, 1 inch cut, and then CL1, and then 2 inch cut plus CL0, 1 inch. There's only one option, 1 inch out, CL0. And then you finally have CL0 automatically just return 0 without referring to our array. And that one, along with P1, it is 1. And then CL1 is returning 1. But before returning 1, it is updating L of 1. L of 1. This one becomes 1. The value is 1 now. This is an index. The value becomes 1 by CL1. And then that P1 plus 1 is 1 plus 1, it is 2. CL1, next, return 0, but P2 is 5, so it is 5. So you have CL2, 2 options, 2 and 5. And then you choose 5, of course, and return 5. But before returning, you're updating our value to 5 here. And then P1 plus 5 is 6. And then this is now how this L is used. So look at this, P2 plus CL1, but CL1 you have a value here. So this one will automatically instantly return 1. And then P2 was waiting, which is 5. So you have 6 without having to go inside. And then CL0 returning 0, along with P3, it is 8. Now you have 6, 6, 8, and then you choose 8, maximum value, return 8. But before returning this 8, CL3 to return, save its own value in R. So this one saves 8. Okay, and then after that, now you go all the way up, and then second option of CL4, and then CL2 doesn't have to go inside because you have the value 5. Value 5. Along with P2, it is 10. CL1, you have value 1. Along with P3, it is 8 plus 1, 9. This is 0. P4 is 9. So 8. No, this is not 8. P1 plus 8 is 9. 9, 10, 9, 9. And this one is returning 10. But before returning 10, you're updating L 10. So L is holding the result of a function. And this option, you don't have any duplication. You are not going inside CL2 twice. You are not going inside CL1 twice. So this is pretty much cut out many branches. And then I see a lot of improvement. And exactly speaking, this one, again, we are counting how many function call you have. Except the first one at the top, you have 1, 2, 3, 4. In this level, you have 4 function call CL. 1, 2, 3. 3 function call here. 1, 2. 2 function call. 1 function call. You have CL5 instead of this. It'll be 5 plus 4 plus this one, this, this. So this one, T of n, is 1 plus 2 plus 3 plus 4 for this CL4. But if we started from CL5, it would be plus 5. So n is a starting point, then it goes up to n. And we know this sequence, 1 plus 2 plus up to n, is same as n plus 1 divided by 2. This is basically big O of n squared. So this is time complexity for this improved version using dynamic programming with memoization. And this is time complexity for naive recursion version, the exponent function. So you see a lot of improvement. Okay, that's it. Thank you for listening, and that is explanation and illustration using the recursion tree. Thank you very much.